Hello. In today's lesson, we will look at some direct current circuits. To begin with, we will look at resistors connected in series. You remember we talked about capacitors in series. Now, how are electrical components connected in series? When they are connected end to end in a closed path. So how are resistors connected in series? Resistors can be combined suitably to produce either a larger value than the ones you have or a smaller value than the ones you have. Now, it can be a series combination or a parallel combination. A series combination or a series connection is an end-to-end connection like this. You have resistor 1 of resistance R1, resistor R2 of resistance R2, and resistor R3 of resistance R3. Look at the way they are connected in series. They are connected from end to end, and the combination is connected to a source of potential. Now, what can be a source of potential? An electric cell is a source of potential. So you can connect the combination to an electric cell. We will now see what happens or what will be the total resistance when we connect resistors like this. So three resistors R1, R2 and R3 are connected in series and connected across a source of potential. Now tell me, what is the total potential drop across the combination? The total potential drop across the combination is V. What does that mean? What is the meaning that the total potential difference is V? It means in order to drive one coulomb of charge from one end to the other, you need to do V joules of work. That's the meaning there. So V joules of work is done to transport one coulomb of charge across R1, and then across R2, and then across R3. That means the total work done is now divided among R1, R2 and R3. So, when resistors are in series, what happens to the total potential? The total potential is divided as V1 across R1, V2 across R2, V3 across R3 in such a way that the total potential V equal to V1 plus V2 plus V3. Alright, let's see. Three resistors R1, R2, R3 connected in series and connected to a source of potential V. V is the total potential drop across the three resistors. Now, suppose V1 is the potential drop across the resistor R1 and V2 is the potential difference across R2 and V3 the potential difference across R3. Then we can say V equal to V1 plus V2 plus V3. I hope that is clear, because V is the total work done to move a unit charge from the left end to the right. That means across each of the resistors. So the total work done is the work done to move it across R1, that is V1, plus the work done to move it across R2, and that is V2, plus the work done to move it across R3, that is V3. So V equal to V1 plus V2 plus V3. But if a current I is driven from the cell, that current I will flow through R1, R2 and R3 without any change. each of the resistors will have the same current flowing in it, and that will be the total current. Is that right? Right. But the current in each of the resistors is the same, which is the same as the total current. So what do? We have the equation V equal to V1 plus V2 plus V3. If you now divide this equation by I, that is common to all those resistors, what do you get? V divided by I equal to V1 divided by I plus V2 divided by I plus V3 divided by I. Alright, can you recall Ohm's law? What is V divided by I? Ohm's law gives us V equal to Ri. Therefore, V divided by I equal to R. V divided by I equal to R, which is the total resistance. Because V is the total potential, I is the total current. Therefore, V over I is the total resistance. What is V1 over I? V1 over I is the resistance R1. V2 over I is the resistance R2. And V3 over I is the resistance R3. Therefore, we have R equal to R1 plus R2 plus R3. So when do we connect resistors in series? When we need a greater resistance than the ones we have. Let's do a simple problem. What is the resistance of a series combination of 4 2-ohm resistances? If you have 4 2-ohm resistors and you connect them in series, what will be the total resistance? Well, the total resistance will be the sum of the resistors. R equal to R1 plus, R2 plus, R3 plus, R4, and that will be 8 ohm. Let's now look at resistors in parallel. How do we connect a number of resistors in parallel? What is the meaning of a parallel connection? If you remember what we did in the case of the capacitor. If I have 2 resistors, now suppose these are the 2 resistors. This is one resistor, this is the other resistor. How do I connect them in parallel? What do I need to do is connect the 2 ends of the 2 resistors together and connect these 2 ends together, and then the system is connected to a cell or a source of potential. Well, when each resistor is connected across the same 2 points, that means if you have a number of resistors and each is connected across the same 2 points, then we have a parallel connection. Now here I have resistor R1, resistor R2 and resistor R3. Notice that R1 is connected between A and B. R2 is connected between A and B. R3 also is connected between A and B. So these 3 resistors are now in parallel. I hope now you understand the difference between a parallel connection and a series connection. So 3 resistors R1, R2, R3 are connected across 2 points A and B, and the points A and B are connected to a source of potential V. That means the potential difference between the points A and B is now V. Tell me, if V is the potential difference between A and B, what is the potential difference across the resistor R1? The resistor R1 is connected between A and B. So the potential difference between A and B will be the same as the potential difference between the ends of the resistor R1. Similarly, the potential difference across R2 will also be the same as the potential difference between A and B, because R2 also is connected between A and B. So, this means that the potential difference across R1 equal to the potential difference across R2 equal to the potential difference across R3 equal to the total potential V. So, one important result you must remember: when resistors are connected in parallel, all of them will have the same potential difference across them, and that will be equal to the total potential. Whereas, when resistors are connected in series, the total potential is divided into the individual resistors. Alright. Now the total current, what happens to the current but? If I is the total current, tell me what happens to the total current when it comes to the position A. When it comes to A, it finds there are three paths that it can go. So a part of the total current will go through R1, another part will go through R2, a third part will go through R3, and when they all reach B, they will all combine to become the same old current I. That means if I1 is the current going through R1, and I2 is the current through R2, I3 is the current through R3, then I equal to I1 plus I2 plus I3. There you are. So the total current is divided in a parallel connection, but the total potential remains the same. So what do? Since the potential is going to be the same for all, we are going to divide this equation by V. What do we get? I divided by V equal to I1 divided by V plus I2 divided by V plus I3 divided by V. Well, I is the total current, V is the total potential. Therefore, what does I over V represent? If you remember, V over I is the resistance R. Therefore, I over V is 1 over the total resistance. So, if R is the total resistance, then 1 over R, I over V equal to 1 over R. I1 over V is 1 over R1. I2 over V is 1 over R2. And I3 over V is 1 over R3. So, if three resistors are connected in parallel, the total resistance R of the combination is given by 1 over R equal to 1 over R1 plus 1 over R2 plus 1 over R3. Now, don't confuse this with the capacitors, because when capacitors are connected in series, the total capacitance is 1 over C equal to 1 over C1 plus 1 over C2 plus 1 over C3. Now the case is exactly opposite for resistors, so take note of that. Resistors are connected in parallel when we need a resistance less than that is available. Now tell me, if I have two resistors R1 and R2 in parallel, what will be the total resistance of the combination? Well, the total resistance can be obtained by solving this equation for R. If two resistors R1 and R2 are connected in parallel, and if R is the total resistance, then 1 over R equal to 1 over R1 plus 1 over R2. Can you solve this for R? Well, the right hand side can be simplified by taking R1, R2 as the common denominator. Then the numerator becomes R1 plus R2. So 1 over R equal to R1 plus R2 over R1 plus R2. Therefore, what is R equal to? R equal to R1 R2 divided by R1 plus R2. A similar situation we saw in the case of capacitors connected in series. Two capacitors in series gives you a total capacitance of C1 C2 over C1 plus C2. Similarly, two resistors in parallel gives you a total resistance of R equal to R1 R2 over R1 plus R2. A very important relation. If you remember, problem solving becomes very easy. A simple problem. A 1 ohm, a 2 ohm and a 3 ohm are connected in parallel. What is the total resistance of the circuit? Alright, well, we go directly to the equation. 1 over R equal to 1 over R1 plus 1 over R2 plus 1 over R3. And R1 is 1 ohm, R2 is 2 ohm, R3 is 3 ohm. So that will be 1 over 1 plus 1 over 2 plus 1 over 3. That is 11 over 6. If 1 over R is 11 over 6, then R equal to 6 over 11 ohm. Now remember, the equation we use for 2 resistors cannot be used for 3 resistors. The equation R equal to R1 R2 divided by R1 plus R2 is only for 2 resistors. You cannot extend that equation for 3 resistors. When you have 3 resistors, you got to come in and use the normal equation. Alright, let's do, so the total resistance actually, when 2 resistors, 2 ohm and 3 ohm are connected, you can see that 1 ohm, 2 ohm and 3 ohm are connected in parallel. The total resistance is less than the smallest of the 3. You see? So when do we connect resistors in parallel? When you want a smaller value than the ones that you already have. Another problem. The current in a looped circuit that has a resistance R1 equal to, the current in a looped circuit has a resistance R1 and the current is 2 ampere. The current is reduced to 1.6 ampere when a resistor R2 equal to 3 ohm is added in series with R1. What is the value of R1? Well, look at the diagram here. The current in a loop circuit. You understand what a loop circuit is? A closed circuit. The current in a loop circuit that has a resistance R1 is 2 ampere. Obviously, the circuit has a cell that provides the potential difference. We are not interested in the value of the potential difference. So, the current in the resistance R1 is 2 ampere. What did we now do? The current is reduced to 1.6 ampere when a resistor R2 equal to 3 ohm is added in series with this. When a resistor 3 ohm is connected in series with it, the current is reduced to 1.6 ampere. We need to find the value of R1. So if V is the potential difference across R1, we can write V equal to 2R1. Is that right? The potential difference across the resistance is V equal to 2R1. Why? V equal to IR. Our I equal to 2 ampere. Alright, now look at the second situation. What did we do? We connected a 3 ohm resistor in series with it. Tell me, what is the total resistance now? When a 3 ohm is connected in series with R1, the total resistance is, alright, tell me what it is. The total resistance is R1 plus 3. When resistors are in series, they add up. So the total resistance now is R1 plus 3, and the current is now 1.6 ampere. Now, has the total potential changed? No, the total potential is provided by the cell. That hasn't changed. So the current now is I equal to 1.6 ampere, but the voltage V remains the same across the combination, and that voltage V is provided by the cell. So can you write an equation for this voltage V when the resistors are, the total resistance now is R1 plus 3? Well, it will be V equal to IR, where R is the total resistance, R1 plus 3. So V equal to 1.6 times R1 plus 3. If you now look at these two equations, V equal to 2R1 for the first circuit, and V equal to 1.6 times R1 plus 3 for the second circuit, V is the same. So what do? We can now equate the right-hand sides. Right. The two equations of V can be used to find the value of R1 by equating the right-hand sides, as 2R1 equal to 1.6 times R1 plus 3. And I'm going to leave that for you to solve, can you? Well, I've got the right step for you. 2R1 is 1.6 R1 plus 4.8, and moving the 1.6 R1 to the left, you get 0.4 R1 is 4.8, or R1 is 12 ohm. That's a good problem, and I would like you to practice this kind of problems. Another one. Find the total resistance between points A and B. That's point A, and that's point B. Find the total resistance between points A and B in the diagram. If the potential difference between A and B is 12 volts. In other words, if I now connect a cell between points A and B of EMF 12 volts, find the potential difference across each resistor and the current in each. Okay, let's first start looking at the total resistance. Where do we start? We start at this parallel combination. Can you tell me what is the total resistance of this parallel combination? When two resistors are connected in parallel, the total resistance will be R1 R2 divided by R1 plus R2. So the total resistance of this parallel combination is 7 times 10 divided by 7 plus 10. So first we find the equivalent resistance of this parallel combination using this formula, R equal to 7 times 10 divided by 7 plus 10, that is 4.12 ohm. So this is now 4.12 ohm. This is now equivalent to a 4 ohm, a 4.12 ohm, and a 9 ohm in series. So now we have a 4 ohm, a 4.12 ohm, and a 9 ohm in series. What is the total resistance? The total resistance of a series combination is the sum of the three. Alright, so this circuit is equivalent to the original circuit. What is the total resistance? It will be 4 plus 4.12 plus 9 equal to 17.12 ohm. That is the total resistance. Okay, now what do we have? We are told that there is a potential difference of 12 volts between A and B. That means there's a potential difference of 12 volts across the combination of resistors. Let's go to the next slide. So if the potential difference between A and B is 12 volts, Well, the potential difference here is 12 volt. And what is the total resistance here? We calculated the total resistance. That will be 17.12, is that right? Now, we have a V equal to 12 volt. The total potential is 12 volt. The total resistance is 17.120. If you know the total potential and if you know the total resistance, can you find the current in the circuit? Well, I equal to V over R. That gives me V is 12 volt, R is 17.120, and that is 0.7 ampere. Now, that means, suppose this is the battery here. Let me go and draw the battery there for you. Now, suppose there's a battery in here. This is A, that's the battery there. And that battery is a 12 volt battery. Now, you must understand what this means is the battery now drives a current of 0.7 ampere. And when it comes over here, tell me, what is the current flowing in the 4 ohm resistor? That 0.7 will flow in the 4 ohm, but when it comes here, that 0.7, part of it will go through the 7 ohm, part will go through the 10 ohm. They will come here, combine to become 0.7 in the 9 ohm. Is that right? Well, I hope you understood that. Well, let's continue. Now, this is the total current in the circuit. To find the current in each resistor, we go to the first diagram. Alright, this is the first diagram. Let's now find the current in each resistor. The total current we know is 0.7 ampere. That means the current in the 4 ohm will be 0.7 ampere. There you are. That is 0.7 ampere. And that 0.7 ampere comes to this point. What happens? Well, let's first of all find the potential difference across the 4 ohm. You know that the current in the 4 ohm is 0.7 ampere. The resistance is 4 ohm. The current is 0.7 ampere. Can you find the potential difference across the 4 ohm? Well, V equal to IR. You know the current, you know the resistance, so that will be 0.7 ampere multiplied by 4 ohm. That is 2.8 volt is the potential difference across the 4 ohm. Alright. How about, let's go now to the 9 ohm. What is the current in the 9 ohm resistor? When this 0.7 comes here, it will split into one part going through 7 ohm, the other part going through 10 ohm. They will combine and will become 0.7 ampere in the 9 ohm. So the current in the 9 ohm resistor is 0.7 ampere. So can you find the potential difference across the 9 ohm? Alright, the potential difference across the 9 ohm is V equal to IR, I equal to 0.7 ampere, resistance equal to 9 ohm, therefore that is 6.3 volt. Now, can you find these two in order to obtain the potential difference across these two resistors? We have obtained the potential difference across the 4 ohm, that's 2.8 volt. We found the potential difference across the 9 ohm, it is 6.3 volt. Now, what is the total potential difference between this 4 ohm and the 9 ohm? It is 2.8 plus 6.3, that is 9.1 volt. What is the total potential? The total potential is 12 volt. And out of that 12 volt, 2.8 is across the 4 ohm, 6.3 is across the 9 ohm, a total of 9.1 volt has been used up. What is the remaining? The remaining potential is 12 minus 9.1, And that will be the potential difference you will see across the parallel combination. And you know that if resistors are in parallel, they will have the same potential difference across them. So this 2.9 volt, which is the leftover, will appear across each of these resistors. So the potential drop across the parallel combination is 2.9 volt. That means the potential difference across the 7 ohm is 2.9 volt, and the potential difference across the 10 ohm is also 2.9 volt. And we can use that now to find the current in the 7 ohm. Can you do that? We know the resistance is 7 ohm. We know the potential difference across the 7 ohm is 2.9 volt. Can you find the current in it? The current in the 7 ohm is I equal to V over R. V, the potential difference across the 7 ohm, is 2.9 volt, and the resistance is 7 ohm, so the current is 2.9 divided by 7, that is 0.41 ampere. Alright, so 0.41 ampere is the current in 7 ohm, and the potential difference across the 10 ohm also is 2.9 volt. Can you calculate the current in it? The current in the 10 ohm is potential difference divided by the resistance. The potential difference across the 10 ohm is 2.9 volt. Resistance is 10 ohm. So that will be 2.9 divided by 10. That is 0.29. So the current in the 10 ohm is 0.29. Now look at this. What do you get if you add these two? What is 0.41 added to 0.29? That is the total current, 0.7. So that works out very well. When the 0.7 ampere comes here, it divides into 0.41 on the 7 ohm, 0.29 on the 10 ohm. They will both combine here to become 0.7, the total current. So now we have obtained the potential difference across each resistor, and we also have the current in each resistor. A very important type of problem. You see, what all we did is to use Ohm's law in solving this problem. Alright, let's do another one. A battery has an EMF E and an internal resistance R. When a 5 ohm resistor is connected across the terminals, the current is 0.5 ampere. When this resistor is replaced by an 11 ohm resistor, the current is 0.25 ampere. Find E and R. Find the EMF and the internal resistance of the cell. Alright, remember, any problem like this can be done only if you know how to represent the problem by using a circuit diagram. Now, what is the circuit diagram like here? A battery has an EMF E and an internal resistance R, and a 5 ohm resistor is connected across the terminals. A current 0.5 ampere flows in it. Alright, here we have a battery. The EMF is E and the internal resistance is R. Now, you know how we represent the internal resistance. This stands for the resistance offered by the cell for the flow of current. So we have a battery of EMF E and internal resistance R. When R equal to 5 ohm and that battery is connected across an external resistance of 5 ohm. And what is the current? The current is 0.5 ampere. Okay. Can you write an equation connecting all this? We have EMF E, the current in the circuit, we have the total resistance in the circuit. What is the total resistance now? The external resistance is 5 ohm, the internal resistance is small r, so the total resistance is 5 plus R. The equation for the whole circuit is, if you remember, E equal to I times R plus R. That is the equation for the whole circuit. So E equal to I times R plus R. Now, use the values there. You got E equal to 0.5, that's the current, times external resistance is 5, and we don't know the internal resistance. We have an equation that contains two unknowns. We cannot solve it. We need another equation. Now, we can find another equation using the scenario given here. What is that? When this 5 ohm is replaced by this 11 ohm. So the external resistor, this is now replaced by an 11 ohm. The current now becomes 0.25. Let's go and make that change. When R equal to 11 ohm, this resistance now is 11 ohm. The current now is 0.25 ampere. Alright, write the same equation for this setup. What is that equation? Again, E equal to I times big R plus small r. The current now is 0.25. The external resistance is 11 and internal resistance is small r. So, we have now two equations. This is the equation for the first circuit, E equal to 0.5 times 5 plus R, and this is the equation for the second circuit. Now, both equations uses the same cell. That means E is the same for both. So what do we do in this case? At the left-hand sides of these equations are the same, namely E, we can equate the right-hand sides. So, the right-hand side of equation 1 is 0.5 times 5 plus R, and that should be equal to the right-hand side of this equation, 0.25 times 11 plus R. I can now leave this for you to solve. Well, simplify the distribute. 0.5 times 5 is 2.5 plus 0.5R is 0.25 times 11 is 2.75 plus 0.25R. And now rearrange the equation. That gives me 0.25R equal to 0.25, or it gives me the internal resistance small r equal to 1 ohm. And to find the EMF, you can now take the value of E to this equation. E equal to 0.5 times 5 plus R. Replace this small r by 1 ohm, and that gives you the value of the EMF as 3 volts. That means the cell we used has an EMF of 3 volts and an internal resistance of 1 ohm. Again, a very important type of problem that you should be able to do. Alright, let's do another example. If the potential difference between A and B in the figure here is 120 volt, find the current in each resistor. Actually, this is a similar problem to the one we did previously. We know the potential difference, the total potential difference, and we can therefore find the current in each resistor. Alright, how do we do that? First, find the resistance of the parallel combination. The equivalent resistance of 100 ohm and 50 ohm. Can you do that mentally? The total resistance of these two resistors in parallel will be 100 times 50 divided by 100 plus 50. Yes, and that's equal to 33.3 ohm. So we have now a 100 ohm connected in series with a 33.3 ohm. So the total resistance of 100 and 33.3 ohm in series now is 133.3 ohm. That is now the total resistance here. and the total potential is 120 volts. Therefore, what is the total current? Total current I is V over R. By now, these things must be part of your system. Total potential is 120 volts. Total resistance is 133.3 ohm. And therefore, the current is 0.9 ampere. That is the total current. That means the total current, if you got the power supply here, the total current comes from the battery. It goes through 100 ohm. That means the current in the 100 ohm will be 0.9. But when it comes to this point, it divides into one part on 100 ohm, the other part to the 50 ohm. We need to find those. Alright, so the current in the 100 ohm is 0.9 ampere, which is the total current. The potential difference, therefore, across the 100 ohm. What is the potential difference across the 100 ohm? The current in it is 0.9 ampere. Therefore, the potential difference across that 100 ohm is V equal to Ri. That will be 100 times 0.9. That is 90 volt. Alright, tell me. What is the total potential we have? Is 120 volts. Out of that, 90 volts occurs across the 100 ohm. Therefore, what is the potential difference across the parallel combination? The potential difference across the parallel combination is 120 minus 90. Alright? The potential difference across the parallel combination is 120 minus 90 is 30 volt. Well, if 30 volt is the potential difference across the parallel combination, what is the potential difference across each of those resistors? What is the potential difference across the 100 ohm? Well, if resistors are connected in parallel, they will have the same potential difference, and that means the potential difference across the 100 ohm is the same as the potential difference across the 50 ohm, which is equal to 30 volt. Now, we can use that now to find the current in each of these. So the potential difference across the 100 ohm, I'm talking about this 100 ohm, is in the parallel network is 30 volt. And therefore the current in it is I equal to V over R. And that will be V is 30 volt, R is 100. So that will be 30 divided by 100, that is 0.3 ampere. Okay, now you tell me, if the total current is 0.9 ampere, and the current that goes in the 100 ohm is 0.3 ampere, what will be the current that goes in the 50 ohm? Well, that will be 0.9 minus 0.3, is that right? When 0.9 ampere comes here, 0.3 goes through 100 ohm, so the remaining must go through the 50 ohm. Alright. Now, since the total current is 0.9 ampere, the current in the 50 ohm is 0.9 minus 0.3 equal to 0.6 ampere. In fact, you can also obtain that by using the equation V over R. The potential drop across the 50 ohm is 30 volt, and so the current in it is 30 divided by 50, and that is also 0.6. You can actually go in any way you want to solve this problem. I want you to practice this kind of problems a couple more times and go and do all the homework problems. Alright, let's do one more. Find the power delivered to each resistor in the circuit shown on the right. What is the meaning of the power delivered? Well, the power in a resistor is the current in it multiplied by the potential difference. Is that right? P equal to V times I. Power delivered is voltage multiplied by the current. So we need to find the voltage and the current across each resistor and then calculate the. So to do that, first of all, let's find the total resistance of this circuit. What do we do first? Remember, the 3 ohm and the 1 ohm are a parallel circuit. So first we find the total resistance of that parallel combination. What is the total resistance of 3 ohm and 1 ohm connected in parallel? You can do that mentally. The total resistance of the parallel combination is 3 times 1 divided by 3 plus 1. That will be 3 over 4 or 0.75 ohm. So this combination has a total resistance of 0.75 ohm. And now this 2 ohm and this is 0.75 ohm and the 4 ohm are all in series. They are now end to end. Alright? So the total resistance of the network now is 2 ohm plus 0.75 ohm plus 4 ohm. That will be 6.75 ohm is the total resistance. Alright. If you know the total resistance, what is the total potential in the circuit? It's 18 volt. Can you calculate the total current in the circuit? The current in the circuit is I equal to V over R. The total current I is the total potential V divided by the total resistance R. Our total potential is 18 volt. Total resistance is 6.75 ohm. That is 2.67 ampere. Okay, from the understanding we developed from doing problems previously, can you tell me if the total current is 2.97 ampere? What that means is the amount of current that comes out of the cell is 2.67 ampere. That means all of that current goes through the 2 ohm. When it comes here, part of it will go through 3 ohm, the other part will go through 1 ohm. They will combine to become 2.67 here, which will pass through the 4 ohm and back to the cell. That's what it means. That means the current in the 2 ohm and the current in the 4 ohm will be the total current 2.67. So the current in the 2 ohm is 2.67 ampere. The current in the 4 ohm also is 2.67 ampere. Now, let's now find the potential difference across each of these resistors. You see, our task now is to find the current in these resistors. In order to do that, we need to find the potential difference. Now, we know that the total potential is 18 volt. If you know the potential difference across the 2 ohm and the 4 ohm, we can take that away from 18, which will give you the potential difference across the parallel combination. That's our aim. So, the potential difference across the 2 ohm, can you tell me what will that be? V equal to I over R. Oh, did I say V equal to I over R? V equal to Ri, where R is 2 ohm, I is 2.67 ampere, and that is 5.3 volt. So the potential difference across the 2 ohm is 5.3 volt. And so what is the power delivered to that 2 ohm resistor? The power delivered is V times I, and you know the potential difference is 5.3 volt. You know the current is 2.6 ampere. So the power delivered to this resistor is 14.2 watt. Alright, now let's go and find the potential difference across this 4 ohm. The potential difference across the 4 ohm will be V equal to Ri. R equal to 4 ohm, I is 2.67, and that is 10.7 volt. Okay, and therefore what is the power delivered to the 4 ohm? Power delivered is V times I. So P equal to V times I, where we just calculated the potential difference is 10.7, I is 2.67 ampere, so the power delivered to the 4 ohm is 28.6 watt. Now what is the potential difference across the parallel combination? We know the potential difference across the 2 ohm. We know the potential difference across the 4 ohm. Add them together and take it away from 18. That will give you the potential drop across the parallel combination of 3 ohm and 1 ohm. So that will be 18 minus 5.3 plus 10.7. That is 2 volt. So the potential difference across the parallel combination is 2 volt. It means, if you now know that if resistors are in parallel, they will have the same potential difference. So the potential difference across the 3 ohm is 2 volt. The potential difference across the 1 ohm also is 2 volt. So potential difference across the 3 ohm is 2 volt. And therefore the current in it, can you calculate the current now? Current I equal to V over R, and that is 2 volt divided by 3 ohm is 0.67 ampere. There you are. So 0.67 ampere is the current there. And what is the power delivered to the 3 ohm resistor? The power delivered to the 3 ohm resistor is P equal to V times I. V, the potential difference is 2 volts. The current is 0.67 ampere. That would be 2 times 0.67. That is 1.34 watt. Okay, now can you tell me what is the current in the 1 ohm therefore? When 2.67 ampere reaches here, 0.67 goes through the 3 ohm. That means 2 ampere must go through the 1 ohm. So the current in the 1 ohm will be 2.67 minus 0.67, that is 2 ampere. Okay, now tell me what is the power dissipated in the 1 ohm. The power dissipated in the 1 ohm will be the potential difference across the 1 ohm multiplied by the current in that. Right. So the power delivered P equal to VI, that is 2 volt multiplied by 2 ampere, that is 4 watt. Now, what is the total power delivered to all the resistors? If you add all that, that will be the total power delivered to all the resistors. And the total power delivered to all the resistors must be equal to the total power supplied by the battery. The battery is supplying the power, the resistors are spending it. Isn't it? The power is dissipated in the form of heat, light, and so on. What is the power supplied by the battery? The power supplied by the battery is the voltage of the battery multiplied by the current that it supplies. What's the current the battery supplies? 2.67. So 18 multiplied by 2.67 is the total power supplied by the battery. Can you do that and let me know if we got it right? If we got the problem right, then the total power supplied by the battery must be equal to the total power consumed by each of the resistors. I'm going to leave it for you to do and let me know how that looks like. We are now going to look at an important concept in electric